In this video, we will talk about normality. That is, evaluating the degree to which a certain set of observations can be said to approximate the normal distribution. To do that, we have three sets of tools, and we usually apply them all. The first way to evaluate normality is to look at graphs. So the graphical evaluation of normality includes looking at the histogram and what is called the QQ plot or quantile plot. The second way of evaluating normality is to calculate certain numerical indices whose values we know for what is really normally distributed. And these are called skewness and kurtosis. And then see if the values we get for our data set deviate from those expected for a normal distribution very much. And the second way to evaluate normality is to run statistical tests of normality. These tests answer a slightly different question. That is, they answer the question, can this set of measurements have come from sampling from a normally distributed population? So let us start by looking at the graphical evaluation of normality. This small data set includes 47 measurements of word reading fluency in grade 1. So there are 47 children. They were asked to read a list of words within 45 seconds. And then at the end of 45 seconds, we counted how many words they read correctly. And as you see, there are some children who didn't really know how to read 0 or very few words. And there were also some children who read quite a bunch of words, almost up to 50. So these are actually pretty good readers for first grade. Now, what does this distribution look like? Does it look like normally distributed? This is a very realistic and reasonable shape to get from actual data. But we need to know whether it is approximating the normal distribution sufficiently well in order to be able to run statistical tests that depend on the assumption of normally distributed data. Let us look into this distribution in some more detail to understand how we evaluate it. The first thing we do is look at the histogram. This looks fairly nice, except for the gap here. It seems that we didn't get enough values between 10 and 15 correct words per minute, whereas the rest of the shape looks kind of okay. Or it could be that there are a bit more values slightly below 10 and slightly above 15. And this is kind of a minor little gap that doesn't really mean that the data aren't normally distributed. So the histogram looks possibly okay. Let us see at the actual values that were obtained, the actual measurements. So each yellow line here indicates one data point. We can see that there was one child who did not read any words. So this child read nothing, could not read any words by the time of measurement in the middle of first grade, really falling behind. There are a couple of children reading 49 words. There are a bunch of children reading 9 words, only one child between 10 and 15, a bunch of children between 15 and 20, and so on. So each yellow line is one data point, and they have been slightly jittered so that you can see more data points when they actually fall on top of one another. This is the normal distribution with the same mean and standard deviation as our data set. So a mean of about 23 and a standard deviation of about 12. And this is a perfectly normally distributed curve. It is not entirely straightforward to directly compare the histogram with this curve, but we can more easily compare the data set with an idealized data set that is normally distributed by taking into account the distances between the data points. So if you look at the data points, the yellow lines down here, you can see that they are distributed such that the first two data points have this distance between them. The second from the third has a slightly larger distance, and then a slightly smaller distance, and so on. So the way to evaluate this is to compare it directly to the distances that would be expected from the normal distribution. Here is a set of 47 idealized values. These aren't actual data points, and they're not randomly sampled from some population. They are mathematically created to have the exact distances that are expected for normally distributed data. So as you can see, the data are more tightly packed around the mean of 0, and they are becoming sparser and sparser as you go farther from the mean. So the largest distances are between the first pair of data, and then the distances get smaller as we approach the mean, tightest at the mean, and then again spreading out. And this rate of tightening and spreading out is exactly equal to what would be expected from the mathematical normal distribution. And these are our actual measurements. These are real data. And what we can do is we can graph these distances in a way that makes it very easily visible whether they are reasonable approximations of each other. So here is what is called a quantile plot. And here is the line on which every point would fall if the distances were exactly the same between the actual data set and the idealized set of values that are normally distributed. The way this graph is created is that we plot each data point against the other. So starting from the left, the lowest value in each of these, we plot one point here, which on this axis has the value from the idealized set, the mathematically expected value. That's why it says here theoretical value. And on the vertical axis, it has the value of the first data point here. So it's 0. And then the next data point links on the horizontal axis here the second theoretical value, on the vertical axis the second actual measurement, and so on for each. This is the third point, and then up to the last point in which we plot the value of the largest theoretically expected point for 47 points with the largest measurement we actually obtained, which is 49. So if the distances between these actual data points were becoming smaller than larger at exactly the same rate as the theoretically expected distances, then all of these yellow data points would fall on the red line. They would form a straight line. And then we would know that our data would be perfectly normally distributed. That doesn't ever happen in practice because data are never perfectly normally distributed, but they're often approximately normally distributed, as in this case, where we can see that the points generally lie very close to the line and do not form another shape that might be distinctly different from a straight line. This is a QQ plot as produced by Jamovi, which is exactly the same as the one I showed you on the previous page. The only difference is that on the vertical axis, it's using the z-scores for the data rather than the raw values. As we know from our z-score calculation, this makes absolutely no difference in the shape of the distribution. It just makes these values more directly comparable with the theoretically expected values. But otherwise, the graph is exactly the same. And by looking at this, we can see that our points fall reasonably close to the theoretically expected distribution, which is indicated essentially by this straight line. So here are 3 different measurements from these 47 children and the corresponding QQ plots on the bottom row. So histograms on the top row, QQ plots on the bottom row. And these are the reference lines. And on the top row, on the histograms, I have added the density lines. So this is the density line for the matrices test. This is the density line for reading fluency in kindergarten, where most children actually cannot read at all, so they get a score of 0. And this is the histogram with the density line for the first grade, which are the data we were looking at, where most kids can actually read somewhere between 20 and 25 words per minute. So if we add the theoretical normal distribution curves with the same mean and standard deviation as each data set, we can look at the comparison between the theoretical curve, the red line, and the actual density of our data, this purple line. So if our data were normally distributed, these 2 lines would be identical. Now they're pretty close. So we can see that the comparison between these 2 curves is very similar to looking at these data points here plotted in comparison to the reference line. This is easier to interpret than comparing these 2 curves. We can see that for the data set in the middle, the shape of the distribution has nothing to do with the normal distribution. And of course, the QQ plot also shows a completely different shape for the data points compared to the reference line. So these data are most certainly not normally distributed at all. And for these data, we see that the 2 curves are reasonably close to one another. And of course, the points on the QQ plot are reasonably close to the reference line and do not form a different shape. So that's how we evaluate histograms and QQ plots. Let us now look at the indices that we can calculate that tell us the degree to which a distribution has properties that are similar to those of the normal distribution. These are data that are theoretically created to be perfectly normally distributed for this sample size of 47. And as you can see, the data fall exactly on this straight line, the straight reference line of the QQ plot, confirming that their distances are as theoretically expected. And this is the normally distributed shape of the histogram, which has the properties that it is symmetric and it is of a certain rate of decline, not too fast, not too slow. This actually, if you look very carefully, does not look perfectly symmetric, but that's because there is an odd number of data points. So at some boundary, one point must go to one of the 2 sides, and that makes one bar look slightly longer than the other one. But the data are in fact perfectly symmetric. So these are normally distributed data. And here we can see the reference line in red. On top here, we can see the individual data points plotted below the histogram. The density line, which is this light purple here, and the red line, which is the theoretical normal distribution with the same mean and standard deviation. And we can already see that although the data conform to the expected distances, the theoretical normal distribution with the same mean and standard deviation doesn't actually have the exact same shape as the density, and that's because you can never perfectly approach the normal distribution with such a small sample, because there aren't enough data far from the mean, because the normal distribution doesn't end abruptly. It never ends. It just drags on to infinity, except with very few data out there. But we only have 47 data points. So these two curves here do not perfectly match, although the data points are perfectly matched to the expected distances. So the two properties that we can evaluate numerically are first the symmetry, and second, the rate of data points as we go far from the mean. So the first one is called skewness. The degree of skewness is the degree to which the distribution departs from perfect symmetry. So a skewed distribution is an asymmetrical distribution. The normal distribution is perfectly symmetrical, and so it has no skewness. The skewness of the normal distribution is 0. So any symmetrical distribution will have a skewness of 0, whether or not its shape is at all similar to the normal distribution. The second index is called kurtosis, and kurtosis evaluates the ratio of points that are far from the mean. Are there enough points at large distances from the mean as we would expect from the normal distribution? Are there too few or too many compared to the normal distribution? So kurtosis doesn't actually evaluate the shape of the curve, but it evaluates whether there are too few or too many data points far from the mean compared to the normal distribution. For the normal distribution, we normalize this value to be 0. So 0 excess kurtosis indicates that there are as many data far from the mean as we would expect. Again, having a kurtosis of 0 does not imply that the distribution looks like the normal distribution. It only evaluates a single property. So skewness and kurtosis are two numerical indices that can be used to tell us if these two specific properties of the normal distribution hold in our data set. If they do not hold, then we know our data aren't normally distributed. If they do hold, we do not know that our data are normally distributed because there could be other deviations from the normal distribution that is not captured by these indices. So that's why we need to use all the different approaches to evaluate normality simultaneously. So what are the values for these data, for this made up, theoretically perfect data set? The skewness is 0 because this was made to be perfectly symmetrical. Kurtosis is not exactly 0, although the distances are exactly as the theoretically expected ones, for the reason that there aren't enough data points far from the mean because the sample is too small. So even though the distances are the right ones, with only 47 points, the distribution is cut too short. And so there is negative kurtosis. Negative kurtosis means too few data points far from the mean, whereas positive kurtosis would indicate too many data points far from the mean. However, this is a very small number. So it is not as far from 0 as 1. In general, skewness and kurtosis between -1 and 1 are considered to be close enough to what would be expected from normally distributed data. So in general, we do not worry if we see skewness and kurtosis between -1 and 1. So these values are consistent with normal distribution, which is a relief because these data were made to be as perfectly normally distributed as possible with n equals 47. On the bottom here, I have also indicated a statistical test of normality that is called a Shapiro-Wilks test. A Shapiro-Wilks test produces two numbers. One is an index called W that varies between 0 and 1, 0 indicating that the distribution is completely unlike the normal distribution, and 1 indicating exactly like the normal distribution. However, we do not interpret this number directly. The reason for that will become clearer after we've discussed sampling. But for now, you should remember that when we evaluate the results of a Shapiro-Wilks test, we do not refer to W, but we refer to P. The p-value is the probability that a distribution like this one could have arisen by random sampling from a normally distributed population. So this test is answering a different question. The question is, could we get a shape like this if we were sampling from a perfectly normal distribution? And so if this value is large, it's a probability, so it will be between 0 and 1. If it's a large value, here it's the largest value possible, and indicates that this data set is consistent with sampling from a normal distribution. Of course, this is a relief because these were data that were made to be perfectly normally distributed for the sample size. So we get perfect values for W and P. If this value is smaller than 0.05, this means that it would have been unlikely to obtain a distribution such as this from a normally distributed population. In that case, we would say that our data set fails the Shapiro-Wilks test, and that our data are not likely to have come from a normally distributed population. But in this case, we get perfect indices consistent with the perfect data. Let us look at a variation now. What about asymmetrical data? This is a slight asymmetry. These are left skewed data. So there is a skew on the left side, like the data are kind of leaning. They're not symmetrical, but this is not a huge deviation from the symmetry. We can see the effect very clearly on the histogram, and we can see it clearly on the QQ plot, because we see that the dots now do not form a line and aren't dispersed around the line, but rather they form a curve on the right side of the reference line, which indicates left skewness. Here are the reference curves for both the histogram and the QQ plot in red. And we can see that the density is slightly skewed, consistent with the histogram, and we can see that the data points have some more values to the left of the most dense area here. What are the indices associated with this shape? The skewness for this data set is minus 0.73. So minus means that the data are skewed to the left. It means that it is on this side that the data drag on. And this is the side that is more abrupt. 0.73 is closer to 0 than 1. So it's between -1 and 1, which indicates that the skewness is mild. It is not a serious deviation from normality as far as skewness is concerned. Kurtosis for this data set also comes to 0.73, which is between -1 and 1, indicated that it's not a serious deviation, and is positive, indicating that there is a slight excess of distant data points, and this is mostly because of this data point, which is a bit far from the mean given the size of the sample. The Shapiro-Wilks test produces a probability of about 25%, 26%. W is very high, is near 1, and P is also quite high, so 26% for a set of data with this shape or a more extreme one to have come from sampling a perfectly normal population. Therefore, this data set does not fail the Shapiro-Wilks test for normality and is sufficiently normally distributed for these criteria, all of these criteria. So skewness is within -1 and 1, kurtosis is within -1 and 1, and the Shapiro-Wilks probability is greater than 0.05. This doesn't mean that we accept our data as normally distributed. It means that these three criteria are fulfilled. We pass these three, but we still have to contend with the QQ plot and the histogram, which suggest a mild deviation. And in this case, there are some times where we might want to correct this deviation and other times that we might not want to. This is the exact same situation, except now that the skewness is on the right side. So this is a right skewed data set. So it's asymmetric. There are excess distant values on the right side, and the QQ plot is curving upwards. It's forming a shape that is distinctly different from the reference line, however, not very far from it. So this is not a clear violation. It's a mild deviation. Here we can see the reference curves in red, and we can see that the density is reasonably close to the normal distribution with the same mean and standard deviation, with this exception. And we can see that the numerical indices are the same because these are the same data, but symmetrically mirrored on the other side. So now skewness is positive, is plus 0.73. Kurtosis is, of course, the same. And the Shapiro-Wilks test also is the same because the shape of the distribution is the same. Let us look at a more severe deviation, so more skewed data. These data are skewed to the left again. And so we have a more obvious deviation here. The curve formed by these points on the QQ plot starts to depart substantially from the reference line. And here are the reference curves in red. And we can see that both the density here and the line here are getting a bit far from the theoretically expected lines. And the indices now are a larger negative skewness. So it's almost -2. It's outside the range of -1 to 1. So this is moderate skewness to the left because it's negative. Kurtosis is very large because of this data point, which is very far from the mean compared to what would be expected for 47 points. And we can see that the Shapiro-Wilks W is now much lower than the previous cases. And this one, which is what we should be looking at, the p-value for the Shapiro-Wilks test is much lower than 1,000. So it is much lower than 0.05. It is actually a very small number, which means that it is very unlikely to get a shape like this if you sample a normally distributed population. It's not impossible, but it's unlikely. So this data set fails all three tests. It doesn't pass any of these criteria. So this data set is most certainly not a good approximation to the normal distribution. And this is the same on the other side. So a right skewed, moderate deviation, moderate skewness. We can see here the reference curves and the indices and statistical test that have the same values, except the skewness is now positive. What about an even more extreme deviation from normality? This data set produces a density curve that is markedly different from the reference normal distribution, and the data are now quite far from the reference line. There is a clear curve formed, so the data on the QQ plot do not look like a straight line at all. They're not scattered around the reference line. Instead, they form a clear and sharp curve that curves away from the reference line at both ends. And consistent with these observations, we see that there is high right skewness, so this is positive and greater than 3. Very high kurtosis because there is a data point very far from the mean, much farther than would ever be expected for 47 data points. And accordingly, the Shapiro-Wilks test produces a low W and a very, very low probability. The number is actually much smaller than that. But all we need to know is that it's smaller than 0.05. So this artificial data set clearly fails the test of normality. It is not approximately normally distributed. Here is another artificial data set. This one is symmetric, but is made to look chunkier. So it doesn't gradually fall off as you might expect for normally distributed data. It's bulkier, and this you can see on the QQ plot because of the way that the points trail off the reference line, indicating that it starts off too steep and then it goes off too steep again. And these are the red reference curves where you can see that the density of this distribution approaches the normal distribution but gets flat here because it rises too fast, then stays high for too long, then drops too fast in comparison to the normal distribution. However, this doesn't look like an extreme deviation. What are the indices for this one? Skewness is 0 because this is a symmetric distribution. Kurtosis is -1 point something. So it's at the limit for being acceptable. It is borderline acceptable. And it's negative, meaning that there aren't enough data points far from the mean. Indeed, because this mountain here, this mountain of data is cut short and there aren't any values where they would be expected for a normal distribution. So this data set fails the kurtosis test, but only very mildly. If we look at the Shapiro-Wilks test, we get a high W and a very high P, 10 times higher than the limit of 0.05. So we pass the Shapiro-Wilks test for normality, meaning that it would be quite plausible to have obtained a set of values like these by sampling from a normal distribution. So if we had this data set, we would normally not need to do anything about it, even though we have a borderline kurtosis value. What about this situation? This doesn't look very normally distributed because it looks very pointed. And indeed, we have a somewhat worrisome QQ plot that suggests that the line formed by the data deviates systematically from the reference line. Let us look at the comparison between the density and the reference normal distribution. So this data set has a lot of values farther from the mean than expected, and also a lot of values around the mean. What are the indices for this? Skewness is 0 because it's symmetric. Kurtosis is in excess of 1. So it's again a mild deviation, but it's outside of the limits -1 and 1. The Shapiro-Wilks test is actually not worrisome. We don't fail the test with a high p-value of 0.45, indicating that it is not unlikely to obtain this shape by sampling from a normally distributed population. This does not mean that our data are a good approximation to the normal distribution, but we need to evaluate further if there's something to do about it. And with these indices, in most cases, we wouldn't actually need to do anything in order to obtain reliable results. So we would probably not act on this value of kurtosis alone, although the shape of the QQ plot is not exactly reassuring. And we should take that into account in the interpretation of our findings, that there is a mild violation of the normality assumption here. What about these data? We can see that this is a more extreme version of the previous set, where we have a very pointy histogram with many values near the mean, and also a lot of values spread out from the mean. And we can see that the line formed in the QQ plot jumps off the reference line at both ends. And the density is too flat here and too pointy here. And again, too flat here. The indices associated with this distribution are zero skewness because it's symmetric, and a kurtosis of positive 2.3. So this is a moderate deviation from normality, which is substantial. And in this case, the Shapiro-Wilks test indicates that the probability of obtaining a data set of this shape by sampling from a normally distributed population is actually quite low, is less than 0.05. It's 0.03. So this data set fails the Shapiro-Wilks test, and we can say that these data are not normally distributed. Let us now look at some actual data sets. All the previous data sets we looked at were created to produce these special situations, so you can train your eyes a little bit on what shapes of data are associated with what values of the indices and the tests. What about our real data? Here is a histogram of real data with the associated QQ plot. Both the histogram and the QQ plot look somewhat noisy, but they do not seem to indicate significant deviations from the normal distribution. Indeed, if we compare to the reference curves, we see that there is some deviation here, but doesn't look like very much, and the same is the case down here. The indices are plus 0.23 for skewness and minus 0.52 for kurtosis. Both of these are well within the limits of -1 to 1 and do not cause concern. The Shapiro-Wilks test also indicates no cause for concern, as the p-value is 0.39. So we can accept this data set as sufficiently close to the normal distribution for the purpose of statistical analyses that require an assumption of normality. Here is another set of real data, and this is the one that really doesn't conform to the normal distribution, as most children receive the score of 0, and therefore the density of the data has nothing to do with the normal distribution curve. And also the QQ plot suggests a completely different shape for the data points than the reference line. Indeed, the indices for this data set are a very large positive skewness of 2.2, a very large positive kurtosis of 3.9 because of all these values far from the mean, and a quite significant Shapiro-Wilks p-value well below the limit of 0.05 due to this deviation from normality and the low W at 0.5. So this distribution fails all tests, the visual ones, the indices, and the statistical test, and these data are in no way normally distributed and cannot be used in any analysis that requires a normality assumption. Here is another real data set. These are the same reading fluency values that we saw before, but in a histogram with wider bars. And we can see that both the histogram and the QQ plot don't look exactly like the normal distribution, but don't look severely different from it either. And the indices associated with this one are a slight positive skewness of 0.2 and a negative kurtosis of minus 0.5, both of which are within the range of -1 to 1 and therefore are no cause for concern. And likewise, the Shapiro-Wilks test produces a very high W and a high p-value of 0.53, which is well above the criterion of 0.05. Therefore, we can use this data set in analyses that require an assumption of normality. Here is one more data set, another realistic data set, actual data. And in this one, we see something a little strange. The QQ plot doesn't look horrible, although we have some deviation here. This in itself is no cause for concern. However, this data set looks more like it has two peaks rather than a single one. And it doesn't look like this is caused by a small gap somewhere where there is a slight dense region of extra values and a slightly less dense region with fewer values adjacent to it. This looks like a real two-peak situation, which is a substantial deviation from the normal distribution. What are the indices associated with that? Well, we have essentially no skewness. 0.06 is an essentially symmetrical distribution. However, we have a lack of values away from the mean. So as the kurtosis is farther from 0 than -1, it's -1.3. This is only a mild deviation actually, but we also fail the Shapiro-Wilks test as the p-value is less than 0.05. It's 0.035, and this is caused by the double peak situation. So in this case, we would not reject this set on the basis of the QQ plot or the skewness. We would only put a question mark based on the kurtosis, but the histogram in conjunction with the Shapiro-Wilks test are actually a cause of concern in case of analysis requiring a normality assumption. Unfortunately, there is not much one can do with a bimodal distribution, so if it has more than one peak. So in some cases, we might be forced to use these data as they are, but we would need to discuss the implications of the violation of the normality assumption in interpreting our findings. To sum up, we often need to evaluate whether our data set conforms to the expectations for normally distributed data. This is because many statistical procedures assume that the data are normally distributed. That is, they have been sampled from a normally distributed population and aren't a weird sample of it that actually is far from a normally distributed shape itself. We generally need to evaluate normality with all of the data we collect. And as we saw, there are three ways to do that, and the three offer different kinds of information, so we should carry out all three of them. The first one is the visual appraisal of normality. This means we look at the histogram, we look at the QQ plot, and evaluate the degree to which they may indicate deviations from the normally distributed shape. The second one is to calculate indices, the values of which are known for the normal distribution. And the common indices of this sort are skewness and kurtosis. Skewness evaluates whether a distribution is symmetrical, and kurtosis evaluates the proportion of data far from the mean. If the values of these indices is not within -1 and 1, then we have reason to be concerned that our data aren't sufficiently normally distributed. if the values are within -1 and 1, there could still be problems with our distribution, but the specific properties that are assessed by these indices are not violated, are not far from what is expected for normally distributed data. Finally, there are statistical tests of normality, and a commonly used one, but not the only one, is the Shapiro-Wilk test. And for this test, we'll look at the p-value and conclude that our data violate the normality assumption if the p-value is less than 0.05, whereas this test is passed if the p-value is equal to or greater than 0.05. But in the end, we have to draw a conclusion about our data based on all three kinds of evaluations taken together in conjunction with the specific requirements of the tests we need to run. And if our data are not sufficiently close to the normal distribution, then we may need to decide to run different kinds of statistical tests that do not depend on the normality assumption.